we're going to now work a problem that requires the vector form of Coulomb's law to calculate a force. And of course, the vector becomes useful when you go to 2 dimensions. We've done enough one-dimensional problems where you can really just look at the magnitude. Now we need to do a 2-dimensional vector problem. So this is one from the book. 4 identical charged particles with 10 microcoulombs of charge are located on the corners of a rectangle with length 60 centimeters and width 15 centimeters. So calculate the magnitude and direction of the force on the charge in the lower left corner. Okay, so to start any problem like this in physics, you need a coordinate system. You always start with a coordinate system. So we are going to do this in Cartesian coordinates because they're a rectangle, so that kind of makes sense to go with standard Cartesian coordinates. Let's see, it said they were on a rectangle 60 centimeters wide and 15 high. So here's one of the charges. Let's go ahead and put one at the origin. That makes sense. And put another one here. And then that can be the 60. I'm going to put 0.6 meters down there. And then the other part of the rectangle was shorter. And this isn't quite to scale, but I'm going to call that 0.15 meters. It's not even close to scale. So there's your rectangle. And there's your 4 charges. The next important thing to do in these problems is to label those charges. Even if the problem didn't label them, you need to label them to keep up with all those forces. So I went with 1, 2, 3, and 4. And in this problem, one nice thing is that the charges are all equal. All equal to 10 microcoulombs. 10 times 10 to the minus 6 coulombs. So that's the first thing you need to do to set it up. And then they ask for the force on the lower left charge, which is the one we put at the origin. So now we need yet another notation. We're going to write a bunch of these F 3 to 1, 2 to 1, 4 to 1, but we need just the total force on charge 1. I'm just going to call that F1. Okay. We're calculating what is the total force on charge 1. And we're going to use that fancy word superposition. So the way electrostatic forces add in this situation is they add. You just sum them. So it's superposition. So what we say then is the total force is the force that 2 applies to 1, F21, plus the force that 3 applies to 1, plus the force that 4 applies to 1. You just add them up. So now we just need to get each one. Let's do 2, 1. And let me put one note. I'm going to do this all MKS units. So I'm not going to write the unit in all the little expressions. I'm just going to, everything is MKS. So I'm not going to write meters and coulombs and newtons and all that. Okay, so F21 equals KE 9 times 10 to the 9 times the charge. And it's actually the same charge, so I'm going to write it squared. So it equals 10, what was it? 10, yeah, 10 times 10 to the minus 6 coulombs squared. Right, but I'm not writing coulombs. Over the separation. So 2, 1 was 0.15 meters squared. Okay. And then we would write r hat 2, 1. And we would see what we get. You plug in all those numbers, you get minus 40 for all these numbers. Or you get 40, I'm sorry, 40. And now we have to think about the direction. And this is an aspect of the problem, sometimes you call it inspection. Which way is r hat 2, 1? Well, you just look at it. 2 to 1, so it's a unit vector along this axis. It points from 2 to 1. There's r hat 2, 1. It points down. If it points down on the y-axis, then the way we would write this in Cartesian coordinates is the unit vector for the y-axis is j hat, but it's down, so it's negative j hat. So just by looking at which way the force goes, we stick that negative there. Minus 40 j hat. So it's a little bit of inspection, just looking at it and thinking about which way everything points. We can also do, very similar, is F41 equals 9 times 10 to the 9 times 10 times 10 to the minus 6. That's 10 microcoulombs squared. Over the separation for this one is 0.6, 4 to 1, 0.6 meters squared. And it's r hat 4, 1. So if you work all that out, you get 2.5 is the magnitude. 2.5 newtons, I'm just not writing it that way. And this one, its unit vector 4, 1 looks like that. R hat 4, 1. Magnitude of 1 pointing that way. So this one is on the x-axis, so that's the I hat direction. And it's negative again, because again, the force is going in the negative direction of the axis. We assumed x was positive this way and y was positive that way. There you go. All right. So again, we're just kind of looking at it and using inspection to decide which way it points. Finally, there's f(3,1). 9 times 10 to the 9, 10 times 10 to the minus 6, quantity squared, over, this distance here. Let's see. So we can get that from the Pythagorean theorem. It's a square root of 0.6 squared plus 0.15 squared. Square root of 0.6 squared plus 0.15 squared. But it's a square root and then it's squared, so I'm just going to leave it alone. I'm not going to jerk it around and square root it and then square it because I'm running out of room. Okay. But this is 0.6 squared plus 0.15 squared in the bottom. And it's r hat 3, 1. All right, so the magnitude of that one is 2.35 newtons. But then, what is the direction? You look at it, I can draw the unit vector, 3, 1, it's like that, r hat 3, 1. But it's not something we can yet put on a Cartesian axis. It's not along a Cartesian axis. So we have a little bit more work to do.